Today we will be solving question number 30 of GATE 2022 chemical engineering paper from the subject of heat transfer. So I will read the question. A perfectly insulated double pipe heat exchanger is operating at a steady state. Saturated steam enters inner pipe at 100 degrees Celsius and leaves as saturated water at 100 degrees Celsius. Cooling water enters the outer pipe at 75 degrees Celsius and exits at 95 degrees Celsius. The overall heat transfer coefficient is 1 kilowatt per meter square Kelvin and the heat transfer area is 1 meter square. The average specific heat capacity of water at constant pressure is 4.2 kilojoule per kg per Kelvin. The required cooling water flow rate is blank. So we have to find the cooling water flow rate, and this is a numerical answer type question, and we have to specify the answer rounded off to 2 decimal places. So the concept related to this question can be found in these references of NPTEL videos as well as web modules. So we can start solving the question. So here we have been given that we are having double pipe heat exchanger. So this is our inner pipe. Let us consider that this is my outer pipe. Okay, the saturated steam enters the inner pipe at 100 degrees Celsius and leaves as saturated water at 100 degrees Celsius. Okay, so let's just assume that this is my steam and T inlet is 100 degrees Celsius, and now it becomes water and T outlet is 100 degrees Celsius. So the water would have condensed in the steam would have condensed in the tube and provided the latent heat to heat our coolant mixture. That is why the phase has been changed from steam to water, whereas the temperature has been remained constant at 100 degrees Celsius. Now cooling water enters the outer pipe at 75 degrees Celsius and exits at 95 degrees Celsius. Okay, so let's just consider that this is my inlet. T cooling water inlet is equal to 75 degrees Celsius and exits at 95 degrees Celsius. Okay, the overall heat transfer coefficient is 1 kilowatt per. Okay, so we have been given the overall heat transfer as 1 kilowatt per meter square Kelvin, and the heat transfer area we have been given it as 1 meter square. The average specific heat of water at constant pressure is 4.2 kilojoule. Okay, so we have been provided Cp as 4.2 kilojoule per kg Kelvin, and we have to find the required cooling flow rate of required cooling water flow rate. So that is this we have to find. Okay. So as in most of the heat transfer problems, we will again write the heat balance equation across the tube. Okay. So the total heat change across my coolant okay, that I can write it as mcp delta T. Okay. M dot C is my mass flow rate of the coolant. Cp we have been given, and this is my delta T. Now in this case, the delta T will be the change in the temperature of my coolant, that is 95 minus of 75. Okay, so that we will just write it as Tc outlet minus of Tc inlet. Now again, this will be equal to the heat that is exchanged from the steam that has been condensed. Okay, so that we can write using the overall heat transfer coefficient as UA, and delta T, but this delta T will be log mean temperature difference. Okay, so we will, okay, and this Q dot C will be equal to Q dot H. So we'll be using these three equation to find our mass fluid. Okay. Now let's just find this log mean temperature difference. For it, we will plot the temperature profile across the tube. Okay. So this is my steam. It enters at 100 degrees Celsius and again leaves as water as 100 degrees Celsius. Whereas for coolant, it enters at 75 degrees Celsius and leaves at 95 degrees Celsius. Okay, that implies my delta T. This one is log mean temperature difference will be equal to delta T1, and if we consider this as delta T2, then this will be equal to the delta T1 minus delta T2 upon ln of delta T1 upon ln of upon delta T2. Okay, so here for the first case we can write delta T1 as 100 minus 75 and delta T2 will be 100 minus 95. Hundred minus 75 will be 25 upon 100 minus 95 is 5. Okay, so we can write it as 25 minus 5 upon ln of 5. So we can solve this and it will give us the value of delta TL as around 12.42. Okay, so this delta T we will be putting it over here and writing the heat balance to find my mass flow rate of the coolant. So let me just put it over here. So for the coolant it was m dot c Cp T outlet minus T inlet is equal to UA delta TL. Okay, and this mass m dot c we have been given it as 1 and Cp we have been given it as 4.2. So we'll just write it over here. The outlet temperature of my coolant was 95 and the inlet is 75. That I will write it over here, 95 minus 75. No, the mass flow rate we have to find. Okay, it wasn't given at as 1, so this you can write mass flow rate of coolant. We have the one was provided as heat transfer coefficient. Okay, so one is my heat transfer coefficient, and then area heat transfer area we have been given it as 1 meter square, and LMTD we have found it in our earlier slide as this 12.42. Okay, so from here we can find m dot c is 12.42 upon 4.2 into 95 minus 75 is 20. So my m dot c will be around 0.148 kg per second. So the mass flow rate of coolant that was asked in the question is 0.148 kg per second. Okay, so this is my final answer, 0.148 kg per second.